The fundamental theorem of algebra. It says if f of x is a polynomial of degree n, where n is greater than or equal to 1, then the equation f of x is equal to 0 has at least one complex root. So we've shown that. Now let's look at the linear factorization theorem. Okay, and this theorem helps us with giving some information, meaning information such as the degree, our actual zeros. This theorem helps us create the equation. So the examples that we've done before, you were given the equation, you were asked to find the zeros. Now you're going to be given the information, we're going to write the equation. So it says if f of x is equal to a sub n is our leading coefficient, remember that, times x to the nth power, plus, and then it proceeds to all the way where we have a sub 0. Okay, so I'll let you read the equation. Where n, meaning our degree, has to be greater than 1, and our leading coefficient, a sub n, does not equal to 0. So I'm going to read this part. It says, where c sub 1, c sub 2, all the way to c sub n are complex numbers. And it says possibly real and not necessarily distinct. In words, it's saying here, an nth degree polynomial can be expressed as a product of a non-zero constant and n linear factors where each linear factor has a leading coefficient of 1. So we're going to, here's some information. For example 4, it says find an nth degree polynomial function with real coefficients satisfying the given conditions. Our conditions are, our degree is 3. We have 2 and 5i are our zeros, actual zeros. And we have a point on the graph at 1 and negative 52. So think about if you were to plot this, you would go the x-axis at 1 all the way to down to negative 52. So we're going to use the linear factorization theorem, the equation f of x is equal to a sub n times x minus c sub 1 times x minus c sub 2. Because how many actual zeros do we have? Now remember, your n is your degree. So that means we're going to have 3 actual zeros. So we're going to have 3 functions here. Excuse me, 3 factors. The word factor. So our third one being x minus, we're going to call that c sub 3. And for our c, okay, it says our complex numbers are possibly real. Okay, so our c, we have 2, and we have another actual 0, which is, it says complex numbers. Now going back to page 83, where it says imaginary roots occur in conjugate pairs. So anytime we have a conjugate, it's going to be plus or minus. So we're going to have a positive 5i and a negative 5i. So we're going to plug these back into our equation. Okay, so we have here f of x is equal to a sub n times, for our c sub 1, we're going to plug in 2. Our c sub 2, we're going to plug in x plus 5i. Our c sub 3, we're going to plug in x minus 5i. Okay? So when you plug in the negative 5i, actually you're going to multiply it to the negative. That's where the plus comes in. Okay? So then we're going to multiply. Let's multiply x plus 5i times x minus 5i. Let's multiply those. And remember, they're conjugates of each other, so the outer and inner terms are going to cancel out. Let's multiply the first. We have x squared. And then our last term, we have here negative 25 I squared. And we know that I squared is equal to negative 1. So this equation becomes x squared plus 25. So now we have here a sub n times x minus 2 times x squared plus 25. Then we're going to distribute, we're going to multiply the x squared plus 25 to the x minus 2, and that's going to give us x cubed minus 2x squared plus 25x minus 50. Alright, so we've gotten to a good point at this moment of finding our terms here using the linear factorization theorem. Now we need to find what is a sub n. Okay, so what we're going to do is we want to find, or to find, a sub n, use the fact that f of 1 is equal to negative 52. So we're going to substitute the values into the equation and solve for a sub n. So remember, we had f of 1 is equal to negative 2. So we're going to, for f of n, going back to our equation, this is our equation, f of x is equal to a sub n times x cubed minus 2x squared plus 25x minus 50. Okay, so we know at 1, think about it, at 1, we have a solution of negative 52. So the negative 52 we're going to plug in for f of x is equal to a sub n, and then for x we're going to plug in 1, substitute 1 in. So 1 cubed minus 2 times 1 squared plus 25 times 1 minus 50. And then we have negative 52 is equal to a sub n times 1 minus 2 plus 25 minus 50. Add those together, we have negative 52 is equal to negative 26 n a sub n. And then to solve for a sub n, we divide by negative 26 to both sides. And our a sub n is equal to 2. Okay, so then to finish, to write our final equation, we're going to plug in, go back to f of x is equal to our a sub n times x cubed minus 2x squared plus 25x minus 50. We're going to plug in the number 2 for a sub n. So we have 2 times x cubed minus 2x squared plus 25x minus 50. And then let's distribute. So our equation now, given that information, okay, those given conditions, our equation is f of x is equal to 2x cubed minus 4x squared plus 50x minus 100.